All right, last time we started section 2.2, which was describing sets. We talked about what a set is, simply a collection of objects, people, whatever it is, a list of things. Elements are the objects that are in that set. And we had gotten to talking about things like null sets, which are sets that have nothing in them. And I believe we're on the word subset. Is that where we are? Yeah, we had done example. Did we do example 4? No, so we're on example 4. Okay, I guess if I flipped to that, I probably would have known. Hey, look, there we go. All right, so I think that I gave a similar example to this last time. So this example 4 says U is a set of all students at OBU, and then A is the set of those who are graduating. And it's asking you in this problem to describe what the complement of A would be. So what do you think the complement of A would be? Yeah, can you be a little more specific, Emily? That's part of it. Oops. You got it. All right, so they are OBU students who are not graduating. So obviously the not graduating part's important. Why did I stop Emily and say we need more information? Why was that not specific enough? Yeah, I still need to be inside of the universal set U, which was the description about being an OBU student to begin with. Make sense? Okay. All right, so this idea of sort of being something that's smaller than the entire group of OBU students, if that's my universal set, is what a subset is. So a subset, if we have a set A and a set B, we would say that B is a subset of A if and only if every element of B is an element of A. And the way that we write subsets is this. Okay, so it kind of looks like a sideways U, or a little bit like a C, but it's kind of squished C with a line underneath it. And what it means is that B is smaller than A, or maybe equal to it, right? It's everything that's already included. Everything that's included in it is included in the bigger set. So let me just describe over here. A, the graduating students at OBU, would be a subset of all the students in OBU. Right? Yeah. It's already contained inside of it. Everything in the set, graduating students from OBU, is inside of the set that's all students from OBU. The notation here actually says that it could be equal to. That's what that line on the bottom is. So, as weird as it sounds, we could say that all OBU students is a subset of all OBU students. It's a super not interesting one. Very not exciting. It's much like writing that 0 is less than or equal to 0. Okay, but like that's weird to write it, right? It's kind of like that. It's technically true, it's just not how we would normally think about it because it's like more than it really needs to be, okay? A proper subset is what we would really mean most of the time when we talk about subsets in our minds. A proper subset means it's a subset and it's really smaller. It's not including everything. There's something that gets left out when you talk about it. Right? So like at my daughter's high school right now, North Rock Creek is first high school, first class of freshmen. There are no sophomores, there are no juniors, there are no seniors. So right now, if we talked about all the students at North Rock Creek, and we talked about all the students at North Rock Creek who are not graduating this year, you'd be talking about the same group of people. Because there are no seniors. They're all freshmen. Make sense? So it would not be a proper subset because they're the same thing. They're describing the exact same thing. However, in most cases, if you were talking about a high school, like let's say Shawnee High School, I can talk about all the students in Shawnee High School, and then I can talk about the students in Shawnee High School that are not graduating. And it's actually smaller than the whole of all the students in Shawnee High School. It's a proper subset because it doesn't include everything. All right? The way that that's written differently is that it's written with that same sort of C notation, You just don't put the line underneath it. You lose the ability to say or equal to, right? Like it was a correct statement to write this, albeit weird, but it is not a correct statement to write that. Yeah? Same idea. When you lose that line underneath it, you lose the ability for them to be actually equal to each other. If we're counting subsets, how many subsets there are, the way that we get the actual number of subsets has to do with how many elements are in the set. So if we have n elements in our set, then there is 2 raised to the power of n subsets. One of those is the set itself. Okay? So if we take that set away, that's my -1, then all the rest of them are proper subsets. So we have 2 to the n minus 1 proper subsets. So let me give you an example of how that works, and I'll kind of explain how it would logistically work if you tried to find them all. All right, so numerically, we'll do that first. It says, consider the set of all mathematics faculty members at OBU, and there are 5 of us, okay? First question is, how many subsets of math faculty are there? Well, according to the previous slide, I would take the number 2, and I would raise it to the power 5. That's going to answer the question. So what, do you know what 2 to the 5 is, anyone? Okay, it's 32. Yeah, you can grab your calculator, it'll be fine. It's 32. There's 32 subsets. And one of those subsets is all of everything. It's everybody there, okay? It's everybody in the department. So one of those we would take away if we're talking about the proper subsets. It's simply one less. Now let's actually talk about what that looks like. So I'm going to abbreviate, let's see if I can abbreviate their last names. So Hans, Marsh, Drake, Tucker, Wilson. Oh good, we all have different last name starts. I hadn't thought about it before, but we do. So if I were to create the subsets, all the subsets exist. One subset would be each of us individually. Like I am a subset of the math department. You know, me as a subset, I'm a math department member, me all by myself, okay? So I could list all of us individually out like this. I'm just going to put ... I'm not going to list them all. But how many of them are there that contain only one person? There's 5, okay? I could do subsets that contain 2 people. Maybe I have a subset that contains Hans and Marsh. Or maybe I have a subset that contains Hans and Tucker. And I have to ... that out. And there are not 5 of those. I'm not interested in us counting them individually, but there's a bunch. What else could I do? I could have 3 people in a subset. So I could have Hans, Marsh, Tucker. Or I could have Marsh, Tucker, Wilson. Looks like Monday, Tuesday, Wednesday. And there's a bunch of 3 subsets, right? Again, we're not counting them. I'm not interested. But there's a bunch of them that could be 3 in a subset. What else could I have? I could have 4 in a subset. I could have the collection of all the ladies. Hans, Marsh, Tucker, Wilson. That's all the girls. Or I could have those who've been here the longest. That would, actually, that's the girls. Never mind. I could have those who are the youngest. That would be Hans, Marsh, Tucker, and Drake. Okay, so there's a whole bunch of them that have 4 people. What else could I have? I could have all 5 of us. And there's one more that I could have. Do you know what it is? None of us. Yeah, there's one subset. Again, not a very exciting one, but it's empty. It's the null set. So what that theorem told me is that if I were to list them all out, I would have to list 32 different subsets to get them all. And one of them, this one right here, would be a non-proper subset. 31 of them would be proper subsets. Does that make sense? I don't know about you, but I don't want to list 32 of these things out. So having a shortcut way to do that is a very valuable tool. There are 32 different subsets. 31 of them are proper. But what if we actually know how many subsets there are? So that's our next example. We actually know that there are elements in a set, and there are 63 proper subsets of those elements. How can I find out how many elements that there are? Well, let's think about it sort of working our way backwards. This is one of those working backwards processes, right? I have 63 proper subsets. So how many subsets do I have? Good. So there's 63 proper. There's one more that are actually the number of subsets. There are, 64 subsets. So how can I find out how many elements there are if there's 64 subsets? Right. 64 equals that 2 to the n. And then trial and error works great. This is beyond our scope of algebra for the elementary levels. I mean, it is. But your calculator will work it just fine. 2 to the power 3, 2 to the power 5, 2 to the power 10, whatever it takes. And if you work that out with trial and error, you will eventually find that the n value is actually 6. 2 to the 6th equals 64. So there would be 6 elements. Remember, I've told you before, trial and error is perfectly legit. There's nothing wrong with it. So there's 6 elements that it would be, or to have 63 proper subsets. Okay. Oops. Example 7 and example 8 look almost identical. At least parts A through D are the same. The directions are different, though. The part I just erased is what makes them different. 63. Example 7 asks you about elements. Example 8 asks you about subsets. So write that into yourself as a note. This is about subsets. Example 8. Example 7 is about elements. And we'll talk about how we think about them differently with these particular questions. All right, so we're going to start with example 7, obviously. What we're asked to find on example 7 is in the blank whether I need to say it's an element of the set or whether I need to say it's not an element of the set. Now, the first thing to look at is whether or not the items on the left are even elements. And that has nothing to do with the set on the right. The question is, are they elements? So can you tell me on part A, we encountered this symbol last time. What does that symbol mean? Null set. And do you see the word set? You see it, right? Yeah. The word set means it's not an element. It's a set. Are you with me? This is a set. And if it's a set, it can't be an element. They're not the same thing. A set is a collection of things. An element is a single item within that collection. Now, I'm going to jump down to part D. Not D, C, excuse me. C. The number inside the curly brace is 4. 4 could be an element, right? Like it stands a chance. But once I put curly braces on the outside of it, what's on the left now with curly braces in the set, the number 4 inside of it, is also a set. Okay, so this is a set as well. And if it's a set, because it's in the curly braces, not the number 4, but the curly braces with the 4 inside of it, all of that combined, like the whole deal, that's a set. And if it's a set, then it's not an element. Okay? So the first thing to do when you're looking at is this an element or not is to decide, is it even an element at all? And if it's a set, then it's not an element. And you don't even have to care what's on the right-hand side. It doesn't matter. Not even in the slightest, because the thing on the left wasn't a set or wasn't an element to begin with. Now, B, which is 15, D, which is 16. Those two are elements. We just don't know if they're an element of what's on the right. So now we get to the point where we get to make a comparison and we get to decide, is it an element of what comes next? It's an element, but is it an element of what comes next? So let's look at B and see if we can figure it out. This is set notation, set builder notation, right? We talked about it last time, and we talked about how sometimes it's, more concise is what it really is to write it in set builder notation than it is in a listing method. So this one says, this is all x such that x is 2n and n is an natural number. So what does this statement, n is a natural number, mean? What were those numbers? Somebody said it. The counting numbers, right? So what are the numbers you first learned to count with? 1, 2, 3, 4. Okay? So this right here is describing 1, 2, 3, 4. And I'm going to use those numbers and put it into this notation. So what's going to happen when I take 2 times 1, 2, 3, 4? What am I going to get? What is it? I am, but what numbers specifically am I going to get? I already have natural numbers. Alicia, say that louder. Even numbers. I'm going to get a more specific type of natural number. If I take 2 times 1, I get 2. If I take 2 times 2, I get 4. If I take 2 times 3, I get 6. If I take 2 times 4, I get 8, and so on. I get even numbers, okay? So everything over here on the right-hand side at the moment, all this is a description for even numbers. These are even numbers. So what can you tell me about what's on my left-hand side of this statement? It's odd. So, is it an element of the set on the right? No, it's not. Because the set on the right were even numbers, and it's an odd number. So it is not an element of. But for a completely different reason than A and C, right? Completely different. Let's look at D then. Okay, so on D, it actually writes it in a listing method. What do you notice about these numbers? They're the even numbers, right? And what number are we comparing to see if it's in the set on the left? An even number. So is 16 an element of what comes next? Yes, it is. Okay, so word to the wise. In your homework, the book does not have you justify it. They just say fill in the blank. Put an element, put a not element. That's fine. I'm not going to make you put in the blank why. But you better know why. Because if I ask it on the test, I'm going to ask you to tell me why. All right? You don't get to just do a 50-50, like guessing kind of thing. You have to justify why. On your homework, it won't make you. Okay. So this is element versus not an element. So we're going to shift gears. The questions remain the same. That is, the parts remain the same, but the question changes. The question is now about subsets. Is it a subset? So, in order to be a subset, let me go back to our definition to just remind you. The first thing is that in order to be a subset, it has the word set in it. Okay? So in order to be a subset, first of all, you have to be a set. It's kind of like in order to be a mom, first of all, you have to be a woman. You don't get to do that, right? So what did you say?
Nothing.
Okay. Like there's a precursor to this, right? In order to be a subset, you got to be a set. Second thing is that you have to have this sort of a containment issue. If B is a subset, it means that it has to be contained in A. The stuff in B has to be in A. So let's go back and let's see if we can eliminate anything based on the sets. So we said just a moment ago that the empty set is a set, right? That's a set. What about 15? Is it a set? It's not a set. How about C? Is this curly braces with a 4? Is that a set? That's a set. How about D? Is the 16 a set? No, it is not a set. So B and D aren't sets to begin with. Kind of like on the last problem, some of them weren't elements, right? So 15 is not a set, so it cannot be a set subset because it's not a set to begin with. 16 is not a set, so it cannot be a subset. So 2 of my problems on this one I kind of get for free. They aren't sets. Doesn't matter what happens next. They can't be a subset if they're not a set. How about part A? Part A, we know it is a set. So the question is it a subset? So what do you think? Alicia nodded her head yes. I see some nods. It is. Do you remember the example that I did with all the math people? One more back, sorry. That last example I put, the last subset I wrote down was the empty set, right? And I mentioned it's not a real exciting set, but it's a set. And in fact, it's a subset of, in our case, it was the math department. So this is a subset. Again, not an exciting one. And you can write yourself a note out to the side. The null set is a subset of every set, exactly. And let me kind of justify for you why, although it's going to sound kind of like a funny reason. It's true, but it's going to sound like a funny reason. In order to be a subset, it has to be a set. Is it a set? Yes. In order to be a subset, everything contained inside of it, of which there's nothing, has to be contained inside of the other set. You kind of get it for like by default, right? There's nothing in it. So naturally, since there's nothing in it, technically speaking, it's also nothing inside of the other one. It's an element of it, right? The nothing is an element of the other piece. So it's a subset. Okay, so now we're going to do one that's like for real. Number C, or letter C. The number 4 as a set, because it's got the curly braces around it, is it a subset? Well, it's a set. So what I have to decide is that set, does everything in that set, what's in that set? Just the number 4, right? The only thing in the set on the left is the number 4. Is that element, the number 4, an element of the set on the right? Yes, it is. Which element? Which one? The 1 plus 3 one, right? So it's a funny way to write it over here on the right, and if you don't like it, you can actually change it so you can actually write it out. This would be 3, 4, 5, 6. That's the set that you're actually looking at on the right. So is everything in the set on the left also in the set on the right? Yeah, there's only one thing to check for, and it is. So this is a subset. But again, it's kind of different reasoning than the subset that was the null set that we looked at before. Okay, the last thing that we're going to take a look at today is called the fundamental principle of counting. The fundamental principle of counting, or fundamental counting principle, says if an event capital M can occur in little m ways, and the event capital N can occur in little n ways, then event M followed by event N can occur in m(n) ways. Okay? We actually did an example of this already. I know the m's and n's, it's okay. Let me go back to the example we did and show you how we used it without me talking about it from before. So I'd like for you to go back to our example from last time. Oops, that was here. One-to-one correspondences. When we talked about this, we said, I talked about dance partners or like males and females in the room or something like this. So we had 6 females in the room, and the first guy comes in and he has 6 people to choose from to take out on a date or something like this, right? Do you remember me talking about this? Shake your head. Okay, cool. And nobody seemed to have any concerns, or at least you didn't voice them, with the fact that the first person that comes in has 6 choices, and the second person has 5, all the way down to 1, right? That made sense. And I just sort of plowed ahead and said, so you multiply them and you get your answer, and nobody even asked me why. Isn't that fun? I was so glad you did, actually, because I knew we wouldn't get to the why yet. But the reason why is because of the fundamental principle of counting. There are 6 ways that the first person can choose his person to take out on a date. And there are 5 ways that the second person can. So 6 times 5 would be the number of ways those 2 guys can choose their dates. And you can extend that to all 6 of the gentlemen coming in and choosing. Okay? So let me do an example with you beyond that so you can see it play out. And we're going to make outfits. Okay? So assuming that they all match, because of course that would be the biggest problem with this example is if they didn't all match. Assuming they all match, how many different outfits can be created from 3 shirts, 4 skirts, and 5 pairs of shoes? Okay? So there are 3 separate things I'm putting on, and I can combine them in a variety of different ways to make a technically different outfit. Okay? So what would I do according to the fundamental principle of counting? Yeah, I would multiply the 3 different numbers together. There's 3 things that I'm choosing: shirts, skirts, and shoes. And I would multiply them together. So what is 3 times 4 times 5? It's 60. I would have 60 outfits that I could create. Let's use the same fundamental principle and talk about a trip to our favorite stores. You have 6 favorite stores in the mall. In how many ways can the following happen? The first one, you have only time to go to 3 of them. Okay, so like on the last problem, I have 3 choices. How many different choices do I have for the first store I could go to? 6. So we're going to assume that we're not terribly concerned about like efficiency here. We're just going to stores. We don't have to worry about time because in reality that's not how it really works, right? I mean, we worry about that we go to things in a certain order because, you know, they're next to each other. So of course I'm going to go to those 2 stores back to back. That's not what we're worrying about. We're just going to go to 3 different stores, okay? So after I've gone to one of those stores, presumably I don't go to Bath & Body Works, leave, and then go right back in. Agreed? That wouldn't make any sense. I wouldn't do that. So once I've gone to one store, I don't return, which means how many stores do I have to choose from after I've chosen the first one? 5. And by that same reasoning, I would have 4 after that. So if I have 6 times 5 times 4, how many different combinations, groupings, whatever you want to call them, different ways could I go to 3 of my 6 favorite stores? 120. What if I get to go to all 6 of them? Well, that would give me 6 lines here, right? The first one would be 6. I'd have it all the way down to 1. And what do I get if I multiply these together? 720, which was the same thing I had for my one-to-one correspondences last time with the guys and the dates. Right, 720. All right, last thing we're going to do today. I'm going to give you a real-life example of the null set. A real-life example. And then you're going to create one for yourself. So here is my real-life example. Oops, I need to put this in curly braces so it's a set. My bad. The null set. The birds living in my house. So if I've described this, and this, I've described this in this way, what does that tell you about the birds living in my house if it's a null set? There aren't any. You do not have any pet birds. My mom had pet birds when I was growing up. All they do is make a lot of noise and poop. It's really not a fun pet, I promise. That's my opinion, of course. But I would like for you to write down a null set, create your own for your life. It doesn't have to be living in your house, but something that's a null set that you can describe. Okay? And then I'm going to ask for a couple people to volunteer to share. A null set for your life.
Can you use like in your house
If you want, yeah, you can. I just don't want you to feel like you had to. But you can. Okay, somebody share with us. What's your null set? What's your null set? All right, what do you have, Savannah? The times you've dyed your hair. So you've never dyed your hair. Okay, so that's cool. Okay, so Julie's pointing to Emily, and Emily's really red, so I don't think she wants to share.
It's just a funny one.
Okay, you want to share?
I'm just like, number of boys chasing after me.
You know what? Not gonna lie. Every semester somebody talks about boys when we talk about this question. Yeah, number of boys chasing after you. Well, that's unfortunate. Such a bummer. Maybe next time, right? Is it a bummer though? Yeah, I don't know. It's a good question. It depends on what the boys are like that chase, right? It's true. I've often, what I used to put until we adopted our oldest kids is I used to say the teenagers living in my house. But at this point, that doesn't work for me anymore because I have teenagers living in my house. Anybody else want to share? Oh, wait, Alicia.
The amount of homework I want to do tonight.
Right. Homework I want to do tonight. That would be a 0, right? A null set. Okay, cool. Very good.